In this video, we're going to talk about the sign convention for internal loads in structural members. And by internal loads, we mean the normal or axial forces, shear forces, and bending moments. So we'll start by drawing a 2D beam element, and we will show the normal forces or axial forces, the shear force, and the bending moments. And to facilitate coming up with the sign convention for these internal forces, we're also going to specify the local axes of the member. Remember, the local axes are what define the orientation of an element. Now, before we get into the sign convention, one thing we should keep in mind is that these internal loads are really just representations of the resultants of the stress distribution acting over the cross-section of the member. And these can be assumed variations of stress or actual variations of stress. So for example, if we have a section, we can look at the shear stress over that section, and the resultant of those shear stresses is what we call the shear force. Similarly, we can look at another cross-section where we have some variation in axial stresses over the face of the cross-section, and the resultant of those axial stresses can produce a bending moment depending on the variation. Similarly, we can have axial stresses also are what produces resultant normal forces or axial forces. So now we'll start with the sign convention for axial forces. Or normal forces. And the basic sign convention is that the normal forces are positive if they produce tension on the segment. So we've drawn a horizontal element here, and it's clear that these normal forces, or this normal force, produces results in tension on the segment. So we would call this a positive axial force or positive normal force. And then we can look at the opposite of that. So that would be the case where the normal force produces compression on the segment, and that we would consider a negative normal force. Now, we should keep in mind this rule actually applies regardless of the orientation of the element. So for example, here we have an element that's oriented vertically, but the normal force produces tension on the segment, so we would still consider this a positive normal force. Similarly, you can have a case where the element is oriented at a diagonal. And in this particular case, the normal force produces compression on the segment. Therefore, we would say this is a negative normal force. Now let's talk about the sign convention for shear forces. So we say that internal shear forces are positive when they produce a clockwise moment on a segment. So let's look at another horizontal segment, and we will draw the shear forces at the ends. And in this particular case, these shear forces produce a clockwise moment, right? The couple that's formed by these two shear forces produce a clockwise moment. Therefore, we say this is a positive shear force. And then we can look at the opposite of that. So the case where the shear force produces a counterclockwise moment. And in that case, we will call this a negative shear force. Similar to the axial forces, this rule applies regardless of the orientation of the element. So here we have an element that's oriented vertically. And in this case, the couple produced by the shear force is clockwise. So we would say this is a positive shear force. And we can also look at the case where we have a diagonal element. And in this case, the shear force produces a counterclockwise moment. So this would be a negative shear force. To end, we'll talk about the sign convention for bending moments. And we say that internal moments are positive when they bend the segment concave in the positive direction of the local y-axis. So let's see what that means visually. So we start with our horizontal segment. We show bending moments at the ends. We know that these moments are going to bend the segment as shown in this deflected shape. And you can see that the bending is concave upwards, right? And remember, we defined the positive direction of the local y-axis upwards. So again, the moments produce bending in the segment that is concave upward or concave in the positive direction of the local y-axis. Therefore, we say that this is a positive moment. Now, keep in mind that we define the sign convention of internal bending moments over the segment, not at any end, not at any particular end. So we can also look at the reverse case where the two end moments are in the opposite direction of what's shown on the left. And I think it should be obvious that this would produce bending in the segment that is concave downward, right? So that means that this would be considered a negative moment. We can also have situations where the moments at the ends of the segment are in the same direction. So for example, in this case, we have moments, the end moments are both clockwise. So this produces a deflected shape, and I'm just going to draw it at the center line. This produces a deflected shape that looks something like this. So based on this, we see that in the segment on the left, you have bending that is concave upward or concave in the positive direction of the local y-axis. So this would be considered a positive moment. And then on the right, we see that we have bending that is concave downward. So this would be considered a negative moment. And we can look at the opposite case again. So this is the case where both end moments are counterclockwise. Our center line deflected shape is going to look something like this. And so the left segment is concave downward, so that would be considered a negative moment, and the right segment is concave upward, so that would be considered a positive moment. Show the local y-axis to be complete. Now let's look at the case where we're still considering the sign convention for bending moments, but now we'll look at the case where we have a vertical element. And so one question becomes, which direction does the local y-axis point? Well, in this case, we're going to show the positive local y-axis to the left. And this is fairly typical in a lot of structural analysis software. So, and we're going to draw the bending moments, the bending moments at the end of the segments, at the ends of the segments, as shown here. So that's going to produce a deflected shape that looks like this. So we see that this is the bending over this segment is concave to the left or concave in the positive direction of the local y-axis. So this would be considered a positive moment. And we can look at the opposite case. Right, so we'll still have the positive direction of the local y-axis to the left. And in this case, we will have bending over the segment that is concave to the right or in the negative local y direction. So this would be considered a negative moment.